will continue our discussions on the detection system in atomic absorption. I had shown you in the last slide that the detection system should include the detector, associated power supplies and an amplifier and readout devices. The readout devices include analog meters, digital meters or a strip chart recorder. However, today computers are incorporated in all but the least expensive bottom of the line instruments. While continuing our discussion on the detectors, in the last class I had explained that the intensity of the resonance line emitted by the monochromator is measured with and without the sample in the flame by the photoelectric detector. So, photomultiplier tube is essential if best results are to be achieved in the determination of metals. However, for general use it is desirable to modulate the output of the light source either with mechanical chopper or by supplying the source with AC and or modulated DC, feeding the detector output to an AC amplifier which is rectified before being fed to a meter. In this way any signal caused by the continuous emission gets attenuated or it gets rejected. However, any fluctuation in the flame emission may give rise to an appreciable AC component and it is best to tune the amplifier frequency closely to that of the modulation frequency of the light source. In single beam instruments, the accuracy of absorption is limited to the fluctuation and drift in the light source. Therefore, a double beam technique is preferable. In such instruments, the light from HCl, that is hollow cathode lamp, is split into a sample beam modulated at frequency f, which is passed through the flame, and another reference beam which is modulated at frequency 2f, which is not passed through. This we have discussed in the last class. So, the amplifier signals from the two beams are separated and the ratio is recorded on the pen recorder. The demand for rapid routine analysis of large number of instruments has led to the requirement of digital readout and digital printouts, whose output can be read directly in concentration units, because quite often people do not the operator of an atomic absorption spectrometer would be different from the actual scientist. So, the operator scientist who can read any of the information from the data, but an operator can read more conveniently direct results, that is concentration units. Such devices are used in conjunction with an automated sampling device, so that instrument can work unattended for considerable period of time. The PMT has the ability to transduce radiation into an electrical signal. This and all we have covered in the last class. What I wanted you to understand is the current slide, what you are seeing I have already explained in the last class. So, but just for the sake of brevity, I am putting most of the words into this slide to make it clear to you. So, if we proceed to the readout elements, again we have discussed that lock-in amplifiers have got very important function to measure the response only at a particular frequency, and this frequency is locked. That means, all other frequencies would be rejected from the strip chart recorder. So, the role of computers becomes very important, especially when we look at the multiple types of functions and precautions and the requirement of data handling are taken into consideration. Therefore, most of the commercial instruments being marketed today have a dedicated computer which provides maximum flexibility for data evaluation and signal processing. In addition, computer gives the analyst many other desirable features such as storing of information required for the instrument parameters for many elements. Suppose you want to determine copper, then you just press copper on the periodic table. It will open up a file which will tell you what type of flame is to be used and what is the wavelength, what is the slit width, etc. What is the Beer-Lambert's law range, what is the linearity, and what should be the flame temperature, what should be the gas flow rate, like that. Several parameters required for the analysis can be exhibited just by choosing copper element on the periodic table. Such information can be stored in the microprocessor, and the computer also, apart from giving these technical specifications, it can also provide control over the instrument variables, and it can set variables to optimum conditions. For example, if you want 324.7 nanometers, you can just enter the computer and go for wavelength requirement. Simply type 324.7, it will start using a stepper motor and move the wavelength range to that value. So, such things are possible, such process variables, conditions, etc., can be set by the computer. This also provides other types of analytical calculation, curve fitting, concentration readout, standard addition, etc. And with computer optimization program, even more sophisticated things like background correction, this is very important, and interference corrections are also possible. And therefore, automation becomes very important, and the requirement is in the field, in the areas of agriculture, and then horticulture, soil science, analytical laboratory, material science, metallurgical laboratory, like that. Several things are required where analysis of a large number of samples has to be done. So, a rapid analyzer with a computer for process automation also was introduced somewhere around 1996. The requirement added was an automatic sample changer, a digital evaluator, and printer. So, this also consisted of an automatic diluter, because sometimes you may, when the signal is very high, you may not get the correct reading, high absorbance, then you will have to dilute. So, an automatic dilution facility was provided, and a sample changer, that means after one sample is done, the sample rack should move, or the sampler should, the nebulizer should move from one sample to another sample, that is known as sample changer. We will take a look at it later in electrothermal atomic absorption also. And then this instrument can take up to 200 sample vials and then give a digital readout and a printout also. So, such automation is system became available somewhere around 1996, and then all the stages of an atomic absorption were carried out automatically. The results are printed out directly in concentration units. Modern atomic absorption spectrometers are provided with facilities like operation with auto samplers also, and you will have to program the auto sampler for your requirement. They have the interface capabilities for direct online operation with an external computer also. The spectrophotometer and all peripheral instruments are controlled by a central processor that also provides the printout of a complete analytical report. So, automation in flame basically does not bring any substantial saving of time. Savings of time can only be expected when several elements are to be determined in the same sample solution. For example, the automation in selection of the sample, sucking and transporting the sample solution into the flame does not give you any savings. But when there are several samples to be done, then automation helps. So, usually automation also brings in the precision as well as it facilitates the operation. That means, your results would be more reliable if the machine takes over the process of sampling, atomization, putting it into the flame, etc., so that manual errors are minimized. For atomic absorption, automation is required to change from one element to another. For example, you may like to do copper for the first 20 elements, and then you may want to change the lamp to nickel for the same 20 samples. Then your sample, you have to change the lamp, you have to change the lamp conditions, current, etc., and then you have to change the wavelength, slit, etc., and then start from the first sample to the same 20 samples. So, it is essentially a sequential operation. So, multi-element lamps do offer certain advantages such as change of radiation source, setting of other important parameters such as wavelength, slit, gain, etc., and it can also perform calibration, and it can do the statistical fitting of the data, as these are the things which take most time. These are, and they are time consuming processes, and they are most difficult to mechanize and automate also. So, with the computer all these things have become possible. Therefore, modern microprocessor technology uses stepper motors for wavelength drive and setting slit, etc. They are completely made automatic, and for simultaneous multi-element determination, time dependent absorbance changes are also required. For example, if you want to determine a number of elements in the same sample, sometimes it is possible to run through sample number 1 to number 10 and come back and change the lamp and again go determine another element, or in the same sample you determine all the elements simultaneously and then go to next sample like that. Several possibilities exist when you have to do the number of analysis for different kinds of elements. Now, this increasing shortage of laboratory staff, centralization of laboratories in large agricultural, environmental, biological and clinical research institutes has led to an increasing need for semi-automatic or completely automatic analytical method. This point I have been stressing again and again, because the amount of effort that has gone into automation is something phenomenal, which has not been seen by any of the analytical technique. In fact, it was the atomic absorption spectrometer improvements in AAS that have led to automation in several other instruments such as spectrophotometry, ICP, AAS, etc. So, AAS is the leader where anything that is required in terms of a process control or optimization, data handling, etc., this has led the way. So, in order to meet this need, a number of automatic instruments have been developed, and that we have already discussed. Now, what I want to discuss with you is the technique of flame AAS, because so far we have discussed the instrumentation in the atomic absorption, and now I would like to talk to you about the technique, how to go about doing atomic absorption analysis. So, there are different components. First of all, you have to understand what is actually happening in an atomic absorption and how to measure the absorbance, how to convert it into a measurable signal and concentration readout, but also you should understand the chemistry of atomic absorption. So, the chemical analysis with flame AAS is usually performed just like spectrophotometry. You have to prepare standard solutions of the analyte. That means, you want to analyze copper, you will have to prepare standard copper solutions. There are a number of the instrument manufacturers usually provide a cookbook, which tells you what are the basic requirement for performing the chemical analysis. For example, if you want to determine copper, the cookbook, when you open the cookbook, the information there tells you what is the wavelength required for copper, what is the gas combination, air acetylene or acetylene nitrous oxide, like that, and then what is the slit, what is the linearity range, and in what solution the samples have to be measured. Sometimes you may like to measure the sample in aqueous media, sometimes the standards need to be made in acidic media, like that. All the details are basically given, and the cookbook also tells you what is the typical absorbance of a known concentration, which has been done under laboratory guidance. That is, several laboratories combined together to produce the basic data for calibration. This cookbook contains all such information. The aerosol, so first you have to prepare the standards, and then you have to pass the samples through the pneumatic nebulizer into a spray chamber. Then the aerosol is carried into the flame, where a number of processes take place, culminating in the production of ground state atomic cloud. That is the essence of atomic absorption. The atoms absorb the radiation, and the decrease in the intensity of the emitted radiation is recorded as the absorbance. So, using the absorbance data, a calibration curve is to be prepared, and then you have to aspire the sample, put it into the flame, and refer the absorbance data to calibration curve and find out what is the concentration of the element corresponding to the absorbance what you have observed. It is just like spectrophotometer. Now, this is a process I have prepared the different stages of atomization, and here you can see that here on this side I have put burner nebulizer, and here I have put flame. The processes recorded on the left side of the burner in this area correspond to the nebulizer operations, and in this area the processes are recorded with respect to flame when the sample enters the flame. So, first of all you start aspiring the solution here, and then there are the aspired solution gives you a small droplets and bigger droplets. Smaller droplets get carried into the nebulizer, and then it proceeds to it forms an aerosol. In between, the bigger drops condense and get out, they are collected and thrown out, and the nebulizer, so a sample solution also can be taken up, which forms the aerosol and solution, aerosol of a solution and gas. So, the oxidant gas is coming here, that is air, and then fuel gas comes here. So, all these three are mixed to form the aerosol solution gas, and the flame region. It enters the flame region, and as the temperature increases, the solvent vaporizes and everything becomes aerosol gas, and these liquid droplets become solids, that is all the solvent gets evaporated. At this stage what happens is the real chemistry starts. Sometimes they formed oxides, hydroxides etc. In the flame. These are difficultly melted, they have high melting points basically. So, sometimes the formation of different substances also can take place, and then aerosol, as the temperature increases, the solids will melt, and aerosol melt gas is formed, an aerosol of the melt and the gas. And again we have substances which form very difficultly decomposed, vaporize, because oxides and other things do not vaporize so easily. And there could be some substances which are not so, which are more easily converted into different kinds of molecules. So, that is also not of much use. So, after this the substances will decompose and it forms the molecules. The molecules can get excited to higher energy state, that is to forming excited molecules. These are of no use for AAS, atomic absorption. And then there could be atoms, the molecules will decompose into atoms, and if the atoms pick up electrons, then they form ions here in this box, this way, and then they can also form molecules, radicals etc. in the flame. So, this process is also useless, and the formation of ions is not ideal for our requirement. So, only the atoms we are interested. So, these atoms whatever remain, they get they form the excited atoms, and then the excited atoms can absorb the radiation, and sometimes there is fluorescence also, and that is of no use again. So, the whole process of atomic absorption involves the aspiring the solution to form a aspirated solution, aerosol solution gas mixture, and then aerosol solid gas mixture, and aerosol of melt and the gas, and then these should decompose to form molecules, and from the molecule certain percentage forms the atoms, and these atoms get excited, and if they start fluorescing, again it is of no use. So, this is basically the atomization process. So, you would see that a very small portion of the sample what you are aspirating forms the atoms, remaining all goes waste, because they are of no direct concern to the atomic absorption process. So, you can see that number of reactions also can take place in the flame. For example, this slide I have written MEX, that is metal halide, and X is chloride, bromide, iodide or some other salt. Basically, that is what is dissolved in your sample solution. If you take a sample of copper, dissolve it in HCl, it will form copper chloride. If you dissolve it in nitric acid, it will form a metal nitrate, or if you do it in the sulfuric acid, it may form sulfates, and the reactions in the flame is decomposition of these salts into metal and the salt. The metal gets excited to metal atoms, ions. So, how does it happen? It happens by picking up, by releasing the electron. This is known as ionization, metal going to metal plus positive charge, releasing an electron, or metal can also form another compound Y, react with a another species to form metal MEY type of salt. This is of no use to us. So, hydrated chlorides, carbonates, sulfates, etc., they can form oxides also upon the elimination of HCl, or sulfates, carbonates. At high temperature, the solvent molecules and acid molecules, when they go away, what remains is only the metal salt. It can decompose and react with oxygen and form carbonates, oxides, etc. And phosphates can form pyrophosphates. That is also another possibility. So, suppose you have basically phosphate salts, they can form pyrophosphates. Now, you would imagine that the temperature of the flame would definitely have some important role in the volatilization of the salts, because as the temperature increases, first the metal salt has to decompose, and then for melt, first it should melt, then it should boil, and then it should decompose into constituent components, after which thermal dissociation process of molecules into atoms begins. Before that, it has to melt and then decompose, then the other processes will start. This is a phase where non-spectral interferences can occur, because the flame will have cyanogen, CH, CO and so many other radicals in the flame, and variety of combustion products can also be present. For example, if you are passing acetylene and then air and putting it into the flame, a variety of combination products such as carbon dioxide, carbon monoxide, simple carbon atoms, water vapor, oxygen, hydrogen, hydrogen ions, atoms, OH radicals, OH atoms, nitrogen, NOx, nitric oxides, N2O5, NO2, NO, several types of NOx compounds could be present. And then there will be solvents also. Suppose you have dissolved the sample in a solution and extracted into, let us say, methyl isobutyl ketone, then the solvent also will be there in your sample. So, the solvent and other possible substances also need to evaporate and decompose, forming atoms, radicals, etc. They are formed by the temperature dependent equilibrium reactions, because most of the formation of such compounds are due to simple reactions, but their presence is presence and concentration also is governed by the residence time in the flame. Therefore, they are for the equilibrium constants and other chemical kinetics of the reactions usually are formed by the temperature dependent equilibrium reactions. In principle, flame can be considered as a solvent in which traces of metal atoms are found, which leads to atomic absorption. This is the essence of atomic absorption. The flame is a solvent, not in the general sense of a solvent what we consider, but it is a medium in which traces of metal atoms are found, which will absorb the radiation passed through them. So, the chemical environment of the temperature and the residence time of the chemical species have greatest influence on the concentration of the atoms in the flame. This we have to understand, because all we are interested in atomic absorption is the concentration of atoms, ground state atoms in the flame. So, the other components like this carbon monoxide and hydrogen, they do not have sufficient free energy to reduce metal oxides. You can look up the free energies of such species in standard chemical tables in textbooks, etc. And the amount of energy that is required to reduce metal oxides to metals is very high, and that much of energy is not supplied by the carbon monoxide and hydrogen, etc. Therefore, during the oxidation, the energy released is only free energy is available to reduce more stable oxides. So, the free energy released must be very high compared to the reduction energy, compared to the energy required to reduce the stable oxides. So, C2 and CH radicals are usually found in the lower zone of the flame. You remember that the flame has number of zones in which the lower zone, which is not very high temperature, medium zone, and then diffusion zone, etc. we have discussed earlier, and I am referring to that figure done in the class about 3 or 4 classes before, when we had discussed about the structure of the flame. And now I am again referring to that figure. If you remember that C2 and CH radicals are found only in the lower zones of the flame, and hydrogen radicals remain longer in the flame, and therefore, they play an important part in the production of atoms, because one is through thermal dissociation, and also hydrogen is a reducing agent. So, most of the oxides that are formed, they do get reduced to the metals by the presence of hydrogen atoms which have got a longer stay. The residence time of hydrogen in the flame is longer. Therefore, they are the active species which will decompose your metal oxides, because they reduce them. So, what are the types of interferences? Now, I am going to discuss with you the different types of interferences in atomic absorption, because all the while I have been saying that atomic absorption is almost an ultimate technique where the interferences are minimal and it is an element specific technique. The term element specific technique does not necessarily mean that there are no problems in the analysis, there are. So, what are the types of interference? How does an interference manifest in the determination of a metal? So, what I am trying to tell you is, so long as you are measuring the absorbance of the sample using a standard and you get certain response reading 0.3 absorbance or 0.32 absorbance etc., and you take your sample, if the concentration is same as that of a standard, it must show you the same absorbance like 0.3 or 0.32, but it does not, and we call it interference of the method interference. So, the actual signal what you get is not exactly what is expected. Now, what could be the reasons? In spectrophotometry, we have seen that interferences can occur due to formation of complexes and then association, dissociation, polymerization, pH effect, temperature effect, etc. But here in atomic absorption, we have different kinds of interferences, basically because of the various processes that take place, either during aspiration, during transport, during during their residence in the flame, and also due to spectral aspects. So, we can consider the interferences in atomic absorption from their respective characteristics. For example, the first one I have put is spectral interference, and this could be due to your inability to separate the spectral line. If there are more than two substances which absorb at the same wavelength, there is nothing you can do about it, because you cannot change your resonance line, because it is the intrinsic property of the element. And of course, you can always choose a second resonance line in atomic absorption, but the sensitivity goes down. So, always you should choose the resonance line corresponding to the minimum energy. So, we will discuss more about this shortly. So, there one part is spectral interference and another is transport interference. This is due to the transport of the sample and solvent etc. Then if you refer to the figure what I had shown you here, the solute and other interferences, formation of melts, oxides etc. So, such interferences can also occur due to volatilization. These are termed as volatilization interferences. Then you can have vapor phase interferences, where the chemical species present in the flame, they can give you they can attenuate the interferences, and then spatial distribution, that is height at which you observe the signal, that also can attenuate the signal to a considerable extent. So, we will discuss these interferences slightly in more detail now, because these are all important. One has to understand the basic restrictions that exist in the determination of the element. For example, in the next slide I am going to show you that the spectral interferences in atomic absorption spectrometry occur when the emission wavelength from the primary radiation source or absorption from other element present in your sample, the wavelength of a measurement is same. Then there is spectral interference. So, sometimes in presence of higher concentrations, for example, you want to determine gold in seawater. Gold is in nanograms, all other salts are in grams per liter, especially sodium chloride, etc. And in urine, small thallium in urine you want to determine. Then the concentration of other salts are in grams per liter, whereas your analyte of interest is in nanograms or micrograms. So, substantial line broadening occurs. So, again I have to remind you that line broadening means the attenuation of the signal, that means you will get a lower absorbance value. So, sometimes radiation scattering of the particles in the flame or molecular absorption by chemicals and radicals also introduces spectral interference when there is resonance line overlap. For example, the resonance line is very sharp, but the molecular bands are broad. So, part of the molecular absorbance usually gets measured along with the spectral line. So, such interferences are also possible, because you cannot isolate only the spectral line from the analyte element from the other matrix elements. That is not possible, because monochromator does not recognize an element, it just recognizes the wavelength. If there is radiation in the wavelength, if there is radiation corresponding to the wavelength what you are measuring, if whatever is the source, it will show you an enhancement if it is there. If it is not there, it will show you attenuation. For example, you can take a look at this calcium hydroxide band in air acetylene flame. In the determination of barium, there is calcium hydroxide band, CaOH band is broad, and barium line, atomic resonance line is very sharp, but there will be some amount of absorbance coming from calcium hydroxide band when you are measuring barium. So, the actual signal for barium increases even though there is no barium. So, but it does not happen all the time, it happens only when there is calcium in the along with barium. And similarly, alkali halides cause spectral interference below 300 nanometer. In general, this is a very general statement. For example, sodium chloride, if you want to determine iron, iron in cerium, sodium chloride is a constant spectral interferent. So, when the spectral lines overlap or lie outside the resolving power of the monochromator, the interference is more serious, because it cannot differentiate, and usually absorbance line, what we need the absorbance line is plus or minus 0.005 nanometers. Now, look at this example of vanadium line. This number is 308.211 for vanadium, and suppose you have aluminum in that aluminum along with vanadium, then aluminum atoms also will absorb at 308.215. The difference between these two wavelengths is 0.004, but your monochromator cannot differentiate between 308.211 or 308.215. It will bunch all of them together and measure in absorbance. Similarly, magnesium line and chromium line are having a difference of less than 0.005 nanometers. See here 200 and 203, 0.200 and 0.203, which will give you the spectral interference, because the monochromator cannot handle this. Sometimes I have also told you that transport influences. These transport interferences are caused by the alterations in the mass flow of the aerosol through the horizontal cross section of the flame at the observation height. This depends on the rate of aspiration, physical characteristics such as viscosity, surface tension, vapor pressure and density of the solutions, etc. So, the causes usually include increase in the salt concentration above 1%, and for example, if the salt content in sea water is 3.5, in urine it is about more than 1%, in plasma it is more than 1%, in several other elements allowing metallurgical analysis, the salt concentration could be much higher, and the result is they form greater droplets and reduce the number of atoms formed, which is actually measured. Therefore, there will be attenuation of the signal, that means you will get lower absorbance value. Sometimes you may have organic macromolecules such as proteins and sugars, and these also will influence your absorbance. So, organic solvents usually burn in the flame, isn't it? Organic solvents, when you are introducing along with aqueous solvents, they burn in the flame, and most of the organic solvents burn with exothermic characteristics. That means, when they burn, they give out more heat. So, the flame temperature itself will increase, the number of atoms in the ground state. We have seen in the introductory part of atomic absorption that as the temperature increases, number of free atoms also increases, and this leads to an enhancement of the signal. You can take it either as a positive or as a negative. Suppose you want to determine the element in a given matrix, a solvent, and you can, an organic solvent present without your knowledge can lead to enhanced signal, that is higher absorbance. Sometimes what you want to do is you want to increase the detection limit to still better values. That means, you want to work at very low concentrations, then you can even add additionally organic solvents to increase the flame temperature and produce the atoms. So, the interference is either way, it can be used for constructive as well as non-constructive purposes. So, if the matrix is fixed, then the interference is deleterious. If the matrix is not fixed, you want to develop a method, then you may like to deliberately add and get the higher absorbance for the same solution, that means improve the sensitivity. So, you can take a look in this table that this is for the determination of copper. Suppose you determine in 0.1 molar hydrochloric acid, assume that this is relative sensitivity is some value, I call it relative sensitivity. Suppose you add 40% methanol to the same solution, you will get 1.7 times higher absorbance than 0.1 molar hydrochloric acid. Suppose you take acetone 40%, then you will get twice, the signal is twice, the absorbance value would be twice that. And suppose you do it, increase the acetone concentration to 80% instead of 40%, then the signal gets enhanced 3.5 times, that is 350 times, all because these solvents burn with exothermic energy, increasing the temperature of the flame and subsequently increasing the atomic population, which will result in an enhanced absorbance signal. That is nice, because you can determine improve the sensitivity, go to still lower concentrations. Suppose you take ethyl pentyl ketone, then the signal enhancement is around 2.8. Suppose you take methyl isobutyl ketone, then the signal is 3.9, but look at the last figure, ethyl acetate, it is 5.1, that means 5 times the signal you will get for the same element if you add these organic solvents to the system. You can do it by at the calibration stage itself, or you can do it while preparing the solution. So, now we look at another aspect of solute volatilization. You remember I talked about the formation of oxides, the solute part of the sample that is used for aspiration. It may form oxides instead of decomposing it into atoms, because air is generally for an oxidizer. So, there are several elements of the periodic table which form preferentially oxides and hydroxides when they are mixed with water and at high temperatures. So, they are generally specific and the signal depends upon the properties of the compounds formed. Suppose your hydroxide melts at very high temperature or oxide melts at very high temperature, then the production of atoms would be affected adversely. So, this type of interference can be called as chemical interference. In premix burners, laminar flame volatilization, in laminar flames, volatilization begins as soon as they enter the primary reaction zone. Therefore, the occurrence of interference also depends on the observation height. So, where the analyte can combine with anions or ligands or simply form refractory oxides. Now, I have a slide for this which shows you the effect of observation of height on the determination of magnesium salts. Here you can see that this is the observation height and this is the signal. So, when the observation height is very small, the signal is also small. That means, if you allow the optical radiation to pass at this height, then the signal is very small. If you increase the observation height, let us say to 2 meter, 2 centimeter, 3 centimeter, 5 centimeters etc., then you will get maximum absorbance for sulphate somewhere around this region. Suppose you increase the height still further, the atoms would many other concomitant processes of the flame take place, and the signal decreases, because it is no longer the high temperature zone where the atom population is substantial. Suppose you have chloride instead of sulphate, then what happens? Look at this figure. The observation height is for optimum chloride signal is smaller than the observation height for nitrate sulphate, is not it? For sulphate, optimum observation height is this much from here to here, whereas for chloride optimum height, observation height is only 1/3 of that. This is for magnesium salts. Actually, what we have done in this experiment is, we have taken sulphate and then we have taken chlorides and nitrates and measured the absorbance at, let us say, 1 centimeter, 2 centimeter, 3 centimeter, 5 centimeter height, and recorded the absorbance. So, the flame height where you make the observation depends upon the salts also. And suppose you do the same thing with calcium salts. Again you have a similar process taking place. Sulphate is lower, its optimum height is larger than that of nitrate, and which is still smaller than the chloride. So, observation height is the one which determines the solute volatilization effects. So, I am coming back to solute volatilization effect. I was giving you only an example of this. So, the oxides of group 3 and 4 of the periodic table, they form polymer structures and they decompose more difficultly. So, we will discuss about these things in the next class in more detail.